Hello everyone, my name is Ricardo Gonzalez, and today I will present my work with my colleagues with the title of A Framework to Virtually Validate Quality of Service Contracts in Ethernet-Based Vehicle Data Infrastructures for Automotive Cyber-Physical Systems. I know that the title is a little bit long, but during the presentation I'll try to cover each of those buzzwords. Here is the agenda for my presentation. As introduction, I will cover the trends in the automotive industry and the challenges for the sector because of those. Moreover, I will give some explanations about cyber-physical systems and design contracts. Further, I will explain what are quality of services and the relation to the in-vehicle communication networks. On the third topic, I will present my framework and the approach for the virtual validation of the quality of service contracts. After that, I will come with a use case as proof of concept for the framework, and finally, we will sum up everything in the conclusion. We quite often hear that the future of mobility will be different. There are many new trends coming to the automotive sector, such as the connectivity of the cars, that I show here by connected infotainment, enable the car to be part of the IoT ecosystem, or this novel to come with high autonomous driving functionalities, example highway pilots, traffic jam pilots, or urban taxis. All those new trends are quite often related to cross-domain functionalities, where in the automotive industry, we have normally or traditionally the separation of the domains done by chassis, powertrain, infotainment, and others, example. Most of those new trends are related somehow to the information technology. That means we have an increase in the usage and the complexity of software and the communication channels. The solution for those normally comes from the IT world as well, and because of that, we will reshape the way we build our EE architectures in the future. Here I have some example of some solutions. Here in the first one, I have the service-oriented architecture that makes the separation of services and signals hierarchical in the vehicle. Or here example, we have the usage of high-performance vehicle computers to run those intensive data processing new features. Here we have an example, the use of cross-domain zone architectures in a way that you can optimize our vehicle development. And finally here we have this increase of the usage of Automotive Ethernet that is able to handle this huge amount of data that's necessary for those new features. And we have those new protocols, example the TSN protocols, the time-sensitive networks, that can guarantee the real-time requirements for such systems. As a result of those solutions and all those new complexity, we have even more this awareness of the cross-cutting concern from the features, making quite complex the development of cyber-physical systems. Cyber-physical systems are systems that require co-engineering between multiple fields of expertise. As you can see on that figure, for the automotive cyber-physical system example, we have software, controls, network, and mechanical disciplines. In the last slide, I said that all those new trends coming to the automotive industry, they are quite related to cross-domain functionalities. If you think in the terms of cyber-physical systems, we can think how a change in my software discipline, example, what happens if I change in my software runtime, how that's going to influence my controls stability. And here again, we have the same problem. It's not quite clear where is the border from one to another. So we can say we have a gray zone or some fuzzy here in the middle of those disciplines. The name of that is cross-cutting concern. So it's this idea of how one change in one domain or one discipline could affect the other discipline. One possible solution for that, to overtake those problems of the gray zones, is the usage of design contracts. The usage of design contracts can bridge the gap between the disciplines' interfaces, giving a clear statement of the assumptions and guarantees of the interfaces and interactions. The design contract will give you an assertion for the interdomain exchange of information. As a example, you can think of a control loop that we have some timing agreements between the control design and the runtime environment. For the runtime environment, we can think of our software and our network layers. Any delay or jitter on those layers could jeopardize the stability of my system. And that's why we need some guarantees for the timing properties that we can make sure that our control loops works as expected. In this simple example, I have cited the usage of timing contracts, where timing is a key point in the quality of service for distributed systems. Now we'll talk about quality of services for in-vehicle communications. Quoting a definition for quality of service, we can say, quality of service is a measure of the ability of network and computing systems to provide different levels of services to selected applications and associated network flows. How we can think about quality of services for in-vehicle communications? For in-vehicle communications, we have a composition of inter-ECU communications and intra-ECU communications, where ECU stands for Electrical Control Unit. Inter-ECU communication is related to the communication outside the ECU. For example, Ethernet links or CAN and LIN buses. So if you use this figure to try to understand better, we can think that this black box is a ECU, and every communication that goes through an Ethernet link or LIN or a CAN bus to another ECU that's in the end of those lines is related to inter-ECU communications. Intra-ECU communications are related to the communications inside the ECU. For example, access to a memory block or exchange of information between the base software, the runtime environment, and the application layers. We can say that the timing properties are affected by a composition of those interactions. As example, I said in the last slide, of this controls loop where we have interaction between the networks and the software. So we can think that the stability of my control loop somehow is related to inter-ECU communications and intra-ECU communications, where for inter-ECU communications, we can think about the delays from the sensor to my controller and to my actuator, or when you think inside the ECU, where's my control loop is running, how is the scalability of those tasks. In this table here, I try to summarize or to create a list of quality of services that are related to in-vehicle communications networks and possible contracts for them. So example, for bounded latency, we can think the bounded latency that can be checked by defining the worst case for end-to-end delay, example to the sender to the receiver. Or we can think about delivery guarantee and loss ratio that is related to how reliable is my transmission with an upper bound for the packet losses. If you think about delay variation, we can think about the jitter. And as a contract, we can set a maximum value or a boundary for this delay variation. If you think about order delivery, that's related to the corrected sequence of stream of data. For the authenticity, that's related to the security of my network. And finally, for data integrity, that's related to how correct is my data. Or say in other words, my data is not corrupted. To sum up this slide, we can see that quality of service are no function requirements. And for the next slide, I will present our framework as approach for the validation of those no functional requirements. Here, For the framework to virtually validate quality of service contracts, we start with our collection of the function requirements and the related quality of service contracts for them. With those requirements in mind, we can build our system architecture. Normally, we build a system architecture with our best know-how to fulfill those requirements. If you think about the last slide that was talking about inter-ECU communications and intra-ECU communications, we can think that in our system architecture, we have some simulations related to the network, and that means the inter-ECU communications, and we have some simulations related to the ECU timing. That means the intra-ECU simulations. Here we have two words, the inter and the intra word. A way to couple these two words together is to have the definition of timing models in a way that we exchange the properties from the inter-ECU word to the intra-ECU word. Example here, we can think about the Ethernet communication. Ethernet communication is a no deterministic communication. That means normally we have a normal distribution for the delay of the frames, where normally we have a mean time for the delay and we have some jitter related to this message. Here is one example of one timing model that we can exchange between the network simulation and the ECU timing simulation. Of course, if you want to enhance our simulation tools or to say that our simulation tools are more credible, we can check the boundaries of our system with some error injections. In this level, we already can do some validations of our timing contracts to see if your quality of service contracts or some of them are already fulfilled. Having those time models from the network simulation and ECU time simulation, we can feed our cost simulation environment. For the cost simulation environment, as I'm talking about cyber physical systems, we need to build up a simulation environment that's able to simulate the cyber world and this physical world. Further in the presentation, I'll talk a little bit more our approach for this cost simulation. When we feed our cost simulation with those time models, we can check with our requirements that comes from our function requirement side, and with that, we can check the results of our simulation and to do the validation of our quality service contracts. As you can see, we have here a feedback to the beginning. That means if one function requirement is not met, then we need to build again our system architecture, and we can do again the whole flow. As a proof of concept for the framework that I just presented in the last slide, we are going to use the autonomous emergency braking system as a use case. First of all, how works the autonomous emergency braking system? So the IEEE functionality activates the vehicle brakes when a collision is imminent, despite any reaction by the driver. That means we have our vehicle with the IEEE functionality, and it's detecting if we have a car in front. If this car detects that's going to crash a car in front, the functionality is going to send a message to the driver, say, hey, you have to brake, we are going to crash. If the driver is still doing nothing, the functionality is going to apply some jerk to the brake pads to shake the car to see if the driver takes an action. And if the driver still does nothing, then the IEEE will take full control of the brake systems and is going to brake the car. As a function requirement, we desire that after the IEEE maneuver, the car brakes with a safe distance higher than 5 meters. The question here is how my timing properties in my system is going to affect my function requirement. In other words, how my delays in my communication lines and my intra-ECU communications is going to affect this function requirement. Here in this slide, I explain a little bit the system architecture for the autonomous emergency brake system. The IEEE functionality has a radar that sends messages to a motion controller using an Ethernet link. And as we can see, we have an Ethernet switch in the middle that's responsible for other Ethernet communications as well. The motion controller, when it receives the information from the radar, decides if the car is going to crash or no. And if it's the case that crash is imminent, is going to send a message to the actuator controller to activate the brake pads. This communication here is done by a CAN-FD bus. And again, we have some elements connected to this bus as well. We can see that for the IEEE functionality, we have FX chain. So how to say, we have the radar that sends some messages to a motion controller that sends some messages to actuator controller. And on those lines for communications, we have other elements. That means those other elements are fighting for the bus as well for their functionalities. And the question, how those other elements and how my radar and my motion controller frames are going to affect my whole functionality, because we have some delay related to those communication lines. That's what I want to show in this picture. We have some delays because of this non-deterministic behavior of the Ethernet, and we have some delays because of this non-deterministic behavior of the CAN bus. And here I want to show that we have what I call end-to-end latency. So we have a latency from the radar finally to reach the actuator controller. And as part of our simulation environment, I want to understand what timing properties we have in this end-to-end latency, or how I show here sensor to actuator effect chain, that could lead to a violation of my function requirement, that the distance is above 5 meters. To virtually validate our IEEE feature, we set up this co-simulation environment, where I call co-simulation environment because we have some tools related to the cyber world, example are virtual ECUs that are able to simulate software that is embedded in the vehicle controllers, and we have some tools that are able to simulate the physical world. Here we can see that we have radars detecting the signals from the real world and sending this information to my motion controller. And then my motion controller is going to send messages to my actuator controller. For the timing models, we are using a network simulation environment. We can build up this network environment because we know the traffic that your system architecture is going to handle. Here, on top of just simulating our normal case, we want to understand how we can degrade our communication channels, or how we can increase our delay and our jitter in a way that we are going to have a violation of our functional requirement. That means how bad can be my communication lines that when my car brakes, I closer than 5 meters of the car in front. Now I'm going to present the results from our simulation approach. In this picture here, I want to show how we build our scenario for the simulation. The blue line represents the ego vehicle speed, and the orange line represents the brake torque. The ego vehicle has the IEEE functionality and is increasing the speed over time, as we can see here, going closer to 80 kilometers per hour. For this scenario, we construct in a way that we can have, example, a traffic jam because of construction side. And this construction side, we have a limit speed of 30 kilometers per hour. Because the ego vehicle is increasing the speed over time, it's going to crash the vehicle in front. And that's where the IEEE functionality has to stop the car in case the driver is doing nothing. In our case, the driver is doing nothing. Here, I want to play with the idea of the best case execution time and worst case execution time. So basically, we pick up a best delay case and a worst delay case, and you try to plot the difference in the speed and in the brakes to see how they behave over time. Here it's interesting to see that in this point here, we have no activation of the brake. Then the IEEE detects that's going to crash the car in front. We have this jerk in the brake pads, as we can see here. And then we have the full brake. And we can see, because of this difference of delay between the best case execution time and worst case execution time, for the best case, we have around 18 seconds, the execution of the full brake torque, and for the worst execution time, we have around 20 seconds. That means, changing the delay, we have already 2 seconds difference between the execution of the brake. Thinking now about our functional requirement, I was talking that I wish that my car brakes after hitting the car in front, but to be more precise, I have to brake with a headway distance, so the distance from my ego vehicle to the vehicle in front, higher than 5 meters. And that's what I want to show in this picture. We run many simulations, playing around the delays times, so how we call here differential time delays. And for each time delay, so this is the delay for my effect chain, how close I'm from the vehicle in front. And we can see that if you have the end-to-end delay of 100 milliseconds, so for the whole effect chain, we are going to be with a distance higher than 15 meters. But if you have, example, 600 milliseconds delay, then it's already below these 5 meters. Here I'm showing this in this graph. So we can see for the blue and for the green, so 500 and 600 milliseconds, we have already a violation of a function requirement. So as summary of that, we can see that for our IEEE functionality, for this scenario we build, to have your headway distance higher than 5 meters, that is our function requirement, we have to set up our quality of service or our non-function requirements that the end-to-end delay is lower than 500 milliseconds. Okay, now I'm going to present the conclusions to finish my presentation. So, what we have for the conclusion? This work proposes a framework to virtually validate quality of service time contracts for automotive cyber-physical systems. I showed that the vehicle is a multi-domain cyber-physical system with rich interactions, where it's quite complex to understand where are the borders between the domains and the systems. I show that all the new trends, or most of the new trends coming to the automotive sector, will increase even more the complexity of the vehicle systems, making necessary new approaches for the system validation. I show that the usage of design contracts could help the system development, bridging the gap between the plural vehicle domains. And finally, for the timing properties related to the in-vehicle network communications, I show that the usage of quality service contracts could aid the validation for the system effect chains. Here are my reference, and that's it from my side. Many thanks. Any questions?